This is quite a tricky question on sequences, in my opinion. Write down the total number of cubes in tower 3. Well, I'm going to take it step by step, and I'm actually going to work out tower 1 first of all. So I've just got 1. And then for tower 2, I've got 1 at the top, and then I've got 5. It does tell me there's 1 underneath. I've got 5. So in total, I've got 6. And then for tower 3, I've got 1, followed by 5. And now I need to just think carefully about this very bottom layer. What I'm going to get is I'm going to be constructing here a 3 by 3 grid. This is the grid underneath. And then I've got a cube at either end. So I think that helps because then I've got a 3 by 3 grid. That's 9, 10, 11, 12, 13. So if I add these up, I'm going to get 19 in total, and that's my answer. Draw a plan view of the arrangement of cubes Edith will use for the bottom layer of tower 4. Okay, I think this needs some careful thinking. So I'm going to do it without a ruler. You should really do it with a ruler, I think. But it's quite hard to use a ruler quickly in this application. I'm just going to draw. This is the plan view of tower 1 because I think this is going to help. And then for tower 2, what do? I build on it, and it comes out like this. And then, actually, do you know what? I think doing that in a different color will make it clearer. And then for tower 3, what I'm doing is I'm basically putting one there, and there, and there, and there. And then I'm making it come out this side as well. There we go. I think like doing it this way makes it more clear than if I just went for it. So for the last one, what's going to happen? Well, every time I'm basically kind of building out a little bit. So I think I'm sort of, it's not actually, the rule is not actually clear, which is why I think this is confusing. But if we go with what's going on here, then I think we're going to just add 1 to each little bit like so. And then I'm going to add 1 to the end. So I'm basically just adding a square onto every little adjacent thing. So that is going to be my answer. Like I could shade that in. I don't know, the color was just there to help indicate it. I personally think there are other answers that should be accepted for this because the rule is not stated. So actually there's lots of possibilities, but this is actually the one in the mark scheme. So I'm going to go with that here, but I think this is why this question is a bit confusing. Okay, so I now want to work out the number of cubes in each of the bottom layers. For tower 3, we've already worked it out. It was 13. For tower 4, I could count these now. I could do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Could I have done that more quickly? I probably could have, but I've counted it, counted the squares. Now if I look at this, I see that it's going up by 4, it's going up by 8, and then it's going up by 12. So this does actually fit in because the difference is going up by, the difference of the difference is actually 4. And that's going to help me for part D. Find an expression for the number of cubes used in the bottom layer of tower N. Okay, this is definitely the most challenging. This is a hard question for number 10 in the paper, it's got to be said. But let's go for it. This is actually a quadratic sequence because of what I just said. The second difference is constant. And I don't think it's easy to get that without using a more like a general algebraic approach. And that is to say, it's going to take the form a n squared plus bn plus c. That is a general quadratic sequence. Now, my approach for dealing with this kind of problem is to substitute some numbers in. So when n is 1, I'm going to get a plus b plus c. When n is 2, I square the 2, that's going to give me 4a. I got a 2 here, I write that as 2b. You always write the number first. And then when n is 3, I'm going to get 9a plus 3b plus c. Now it can be shown that this will have a constant difference, like I'm assuming that you've seen this before, so that you're aware of that. If I find the difference between these terms, the difference is going to be 3a plus b here, and it's going to be 5a plus b here. And then my second difference is actually equal to 2a. And it would be 2a over here as well if I did carry it on. I haven't shown that, but I'm just telling you that would be the case. All right, how is that useful? Because I can basically use this with my actual quadratic sequence, and I can set. I should have color coded it a little bit better. Actually, I'm going to change it. So this term here goes with the black terms on top up here, and then this blue term actually goes with the red term above. And this shouldn't really be green. I'm going to change it to purple, but now it's color coordinated. Maybe I should change this to purple as well. Okay, because what can I now do? I can basically say, well, here's the constant second difference, and here's the constant second difference. So 2a must equal 4, and a must equal 2. And I've got my first part of the expression. What next? I then can look at the first difference. I could pick any of them, but let's pick the first one. That 3a plus b must equal 4. But I know what a is, it's 6, so it must be 6 plus b, because 3 times 2 is 6. 6 plus b is 4, and therefore b is going to be minus 2. And I'm nearly there. For the last one, I can just pick a term. Let's pick the first one, 1, and a plus b plus c. A plus b plus c must equal 1. But I know what a is, it's 2. I know what b is, it's minus 2. So actually these are going to cancel, and I'm left with c equals 1. And finally, I can just substitute these numbers into my general quadratic sequence, this one. And I can write down that it's 2n squared minus 2n plus 1. Oh, and this question really escalated, didn't it, from just counting squares to finding the nth term of a quadratic sequence.